Great, thank you so much. I am Jenna Wiens. I'm a faculty member of computer science and engineering here at Michigan and associate director of the AI Lab. And I'm thrilled to be chairing this next session to present our AI Rising Stars. We have Emily Diana up first. She is a PhD student in statistics and data science at the Wharton School at the University of Pennsylvania, working with Michael Kearns and Aaron Roth. Her research focuses on the intersection of ethical algorithm design and socially responsible machine learning. Welcome, Emily.
Well, hello, everybody. I am very happy to be here with you. Today I'll be talking about work with Michael Kearns, Aaron Roth, and Tiffany Deng on balanced filtering via non-disclosive proxies. So algorithmic bias has been featured quite prominently in the news as of late. There was a case where Amazon's resume screening software was discarding resumes with female gender terms in them. There was the ProPublica investigation of the Compass recidivism algorithm that they showed were much more likely to falsely predict that an African-American male would recidivate compared to a white male. And then there's been issues with predictive policing. So when we use algorithms to allocate police to areas where there are more crimes, then more crimes are caught, more police end up there, and then this cycle can be very damaging for many communities. So as an algorithmic fairness researcher, there are several places where we can intervene on these processes. So we could intervene on the data collection stage, on the model choice formation stage, and then on the deployment phase. So once we have the model, once we get its results, what do we do with it? So in this project, I'm looking at the data collection phase. And one of the reasons that an algorithm may exhibit bias, so it's usually not because someone designing the algorithm or designing the system was sitting there saying, let's make sure that no women are hired at Amazon, right? So usually it's some artifact of the data the algorithm is learning from. And one of those artifacts could be that the data is highly imbalanced. So it could be imbalanced with respect to groups like race, sex, age, but often those groups are also considered sensitive features. So we might not be allowed to see them in the data set. They might not be collected on a large portion of the data set. And so it can be tricky if we want to collect a data set that's balanced, say with respect to race, but we can't actually see race when we're collecting that data set. So our strategy is to take a pipeline perspective to this. We imagine that there's some entity that does have access to a small sample of data with the sensitive attribute, and that entity is going to create a proxy function. Now, anyone else that has a much larger set of data without those attributes can use this proxy function to help filter down that data into a balanced subsample. So we represent this proxy as a decision tree. And broadly what happens is that we have, so here I made 3 groups, red, yellow, and blue. And when we apply this decision tree to one of these samples, that sample will get sorted into one of these, say, 4 proxy groups. Each of these proxy groups will be paired with an acceptance probability. So if a red sample gets sorted into proxy group 2, and proxy group 2 has a 50% acceptance probability, that sample has a 50% chance of being included in the data set. But we have to do this in a way where these proxy groups are not too correlated with the original sensitive attributes. Otherwise, we've defeated the purpose of protecting people's privacy in this way. So I'll give kind of a brief mathematical overview of what's happening here. So we take this decision tree and we're going to represent it geometrically as a convex hull on the simplex. And what's happening is each leaf of the tree is going to end up having some breakdown of red, yellow, and blue samples. So within each leaf, we have some probability distribution. So for example, in leaf 1, we may see that 25% of the samples are red, 50% are yellow, 25% are blue. So if I know that you got put in group 1, then I can say with 50% probability, you're yellow. So we can represent these probability distributions as points on a simplex, where the corners indicate leaves that would have entirely red, entirely yellow, and entirely blue. And there's a result that says that if we can grow this simplex to include the uniform distribution, which in this case would be 1/3, 1/3, 1/3, then we can find sampling probabilities that'll give us a balanced subsample. And this is what would happen when we're growing that hull. So we start, say, with this just three-leaf decision tree. So at this point, there are 3 proxy groups. And we're going to look at what direction we have to expand the hull to get to the uniform. We're going to choose a vertex. We're going to split that vertex into 2 vertices. So now we have a tree with 4 leaves. And we are splitting it kind of in the direction of our goal, but it has to be sufficiently non-disclosive. So by making that split, we can't form a new leaf that is, say, 1 minus alpha concentration of a single sensitive group. And here are some experiments. So on the left, we have graphs showing the convergence of this algorithm. So actually, each iteration here also corresponds to a new leaf being formed in the tree. So on the top, we've tested this on the adult data set, on the bottom, on the ACS mobility data set. And what you're seeing here on the left is the distance from that uniform distribution. So when we're expanding that convex hull, how close are we getting to the goal? And then on the right, you see some before and after filtering data in sample. And so both of these data sets were highly imbalanced. We had much higher representation of group 0, group 1. And then after filtering, all groups had about the same representation. And I will stop there.
Thank you, Emily. I'm going to ask our next speaker, Esther, to come up and get set up. And while we are working out a tech solution here, are there any questions? Questions for Emily? So I can ask a question. Sure. So I appreciate the work in terms of privacy concerns and how people might not report sensitive attributes because they don't want you to use them. And you've thought carefully, even including this 1 minus alpha term. Do you have a sense of what alpha people are happy with? So if I could tell with 60%, 70%, 90% probability.
Yeah, so I think that'd be very context specific. And we'll look at a trade-off of different alpha levels and then different levels of balance in the final data set. You would expect there to be some kind of Pareto trade-off. As a statistician, so my home department is statistics, so I would certainly want that with less than 95%, I can say I think you're in this group. That may not be sufficient for some people, but the algorithm designers can, choose that alpha in conjunction with the use case.
Great. Thank you.
Oh, yes.
We just need your mic. And I should say, if you do have questions, you can stop by Emily's poster. So all of our Rising Stars also have a poster in the upcoming poster session over lunch. So please stop by. All right, so our next speaker is Dr. Esther Rolf, who is currently a postdoctoral fellow at Harvard. Her research interests focus on the development of machine learning algorithms for addressing pressing social and environmental problems. Esther completed her PhD in 2022 at UC Berkeley, working with Mike Jordan and Ben Reck. Welcome, Esther.
Thank you. Can everyone hear me? The mic is okay? Great. So it's my pleasure today to share with you a very brief and possibly ambitious in 5 minutes overview of my research. So I study statistical machine learning. And very often in research and education of statistical machine learning, we're thinking about the algorithm box. And maybe we're thinking about data as input and decisions or accuracy as output. But to achieve the societal level benefit that got me interested in this research in the first place, we really need to think about the broader context, the systematic design and use. So in the next slide, I'll give you some examples to make this more concrete in my work with satellite imagery and machine learning, focusing on the specific types of data we can use in that context. as well as the downstream uses of these technologies, and particularly who is going to be able to make those decisions and interrogate these systems. I'll then present some of my research in machine learning more generally with the principle that really achieving benefit, let's actually think about what makes machine learning systems functional. And key components of that function are going to be fair systems and data efficient systems. So one of the key threads of my research is combining satellite imagery and remote sensing data with machine learning, where we have the potential to make global monitoring and data-driven policy really more of the norm. But this type of data comes with key challenges like sparsity or quality resolution of data. So here you see 30 by 30 meter observations of land cover, but we have satellite imagery at 1 meter resolution. And if we can leverage this type of coarse or imprecise data with algorithmic innovations, as my collaborators and I did, we can actually recover high-resolution 1 meter predictions of land cover. This is very much more on the what data gives us and how that contextualizes algorithm design. If we think about who gets to use these types of algorithms and technology, who gets to interrogate them for effectiveness, for fairness, it becomes very important that not only machine learning researchers can use this technology, but a much wider set of scientists. So in this project, we're really trying to make satellite imagery and machine learning as accessible as possible. So rather than starting with a huge amount of satellite imagery, having to store that, training a CNN or very complicated vision model, this system converts the imagery into vectors that then are amenable to linear regression on a laptop. And in a very exciting recent news, this data is available at 1 by 1 kilometer resolution across the globe at the link you see here. So taking systems like that and then coming back to machine learning generally, what do we need for the machine learning systems to achieve their potential for benefit? Well, I would say 2 tenets here. First, they need to be fair, and fairness itself can be a slippery term. In work from 2018, my collaborators and I showed that common statistical fairness notions in machine learning can actually inadvertently harm the groups they were meant to protect, more so than if those fairness constraints had not been applied. In follow-up work, we propose an alternative of welfare-aware multi-objective learning that encompasses some of these traditional fairness notions, but extends beyond them and allows you to more directly and transparently solve for desired impact. Yes, here we go. And if we want to think about making machine learning systems do what we want, if we want them to be accurate, fair, accessible, we need to understand how the input data affects our ability to reach these diverse objectives. So some of my recent work quantified the importance of diverse and representative training data, actually giving a characterization of some reasonable settings where in your training data set, you might actually want to prioritize collecting data from small groups, even in your target or evaluation population. And I'm currently working on how we can make this principle of data efficiency something mathematically and computationally characterizable. So in particular, recent work identifying when we might have inefficiencies between our model class and the data that we're given that might indicate room for model improvement. So in summary, I work to make functional machine learning systems that are fair and data efficient by design. If you are interested in any of these themes in remote sensing, application-driven machine learning for climate conservation and public health, or generally data-focused algorithm design and evaluation, I have a poster and I'm around and I would love to chat.
All right, I'm going to ask our next speaker to come up, Elvis, and then give the audience a chance to ask Esther a question. Come on, I see some of you want to ask a question. I'll come to you with the mic. feel like I'm teaching again. You have a question?
This is just very specific, but because I was thinking about data balancing, noticed your part about data balancing, and you said that we may want to try to, collect more data even from the target population.
Right.
What did you mean by that? Was that just like the minority group?
Yeah, so if you have a population made up of a set of groups, even if you're targeting an average accuracy objective, you have incentive to upsample from those small groups in your training data when you have that lever to pull of how many samples you'd get from each group. Yes, thanks.
Thank you.
Great. And I was wondering if you've considered. I was wondering if you considered any applications in healthcare and specifically medical imaging with respect to the work that you did combining multi-resolution, low-resolution images, since oftentimes the resolution can vary across health centers and countries. So has that ever come up?
That's a really interesting question. That's not something we looked at specifically in that paper. There are just huge amounts of settings where the labels that you get are not actually at the scale that you want to predict. And many in Earth observation, many in healthcare. And our paper goes through maybe like 7 different examples where you can convert these noisy or low resolution observations into actually a prior belief on what would be where in the image. You can learn from that prior belief in the Bayesian sense, treat that as noisy or uncertain labels, and then resolve from that with your high-resolution images, whether they're satellite or medical images, what actually your posterior belief over the actual labels would be. So it would be very amenable to this setting. It's just not one I've looked at yet.
Yeah, I'm thinking there are a lot of applications. So thank you very much.
Yes, thank you.
All right. So next up, we have Dr. Elvis Dohmatob. He's currently a researcher at Facebook AI Research in Paris. His research interests include deep learning and robust optimization. Elvis graduated with a PhD from Université Paris 11 in France in 2017. Later, he joined INRIA and Criteo AI Lab in Paris prior to joining FAIR. Welcome.
Yeah. Thanks for the invitation. So I'm going to present work that was done by myself and my collaborator at NYU, Alberto Bierzi. So it's on trade-offs between test error and robustness error in neural networks. So my work is going to be slightly theoretical, but come to my poster later to have the real stuff. So just to give a general idea, so we are on the same page concerning adversarial examples. So thinking about adversarial examples, you have this image in mind. So this is a photo of a tabby cat, which is rightly classified by a favorite neural network as 88% tabby cat. And you put a bit of perturbation to it. Humans have sufficiently strong inductive bias about what is seen. But the computer thinks it's guacamole, right? So this is really scary. And okay, you can have some other examples where, okay, you have an image of maybe a truck, you distort it by adding some well-crafted distortion, it gets classified as an ostrich or something like that. So this is should be sufficient to destroy the dreams of all the people who think self-driving cars are going to be here next to it or so. What's happening? So there are a bunch of stuff which I understood on this problem at the moment. So it's known that, okay, things like spurious correlations. So in a learning problem, there could be correlations which are good for predicting well, but which don't generalize very well. So some people might know this under the name of weak features. So you might have some features which are present in training, but during tests, they might do some crazy stuff. There is also a work that shows that random initialization, so neural networks are non-convex problems that you start training at a certain point, and where you start actually depends on where you're going to end. So if the initialization is not well calibrated, you might end up with a model which doesn't which is not very robust. You can also have adversarial examples as being natural consequences of normal error. So you should think about this as a snowball effect. So in the classical sense, if you do a small error, so there's a small proportion of dogs which you misclassify as cats. In the adversarial sense, this is going to blow up. Okay, so you can use geometric probability theory to show that in certain feature spaces, if you make an error in a small region of space, then if you look at this from an adversarial setting, this is going to grow up and essentially fill up the space as a function of the size of the attack. Okay, so this is, you could think of this as properties of high-dimensional space. And okay, there are many other things. So for example, many training, you can prove that at least under certain circumstances, neural networks learn in the following way. So first of all, they try to memorize the training data set. And then in the second stage, they try to kind of extrapolate a bit. But there's a big stuff which is less memorized. So they memorize the stuff, and then they do something on top of the memorized model to make it like predictable. What else? Okay, so what is not known is what's the effect of training. When you train the model, what happens? So when you train the model, gradient descent has a certain inductive bias. So it's a bunch of different things which might solve a problem. And if you run gradient descent, it's going to select one of those solutions. And so this inductive bias might have some consequences for robustness. So just to set the stage for what we are going to say, so to understand this phenomenon, we are going to fix a theoretical framework. So we are going to fix a simple problem and try to say something interesting about it. And the simple problem is going to be in the setup of so-called student-teacher. So I'm going to have a network which is a student that generates data as follows. So it draws features IID from isotropic Gaussian in d dimensions, and the label is just a quadratic form. Okay, it's that's simple. And of course, the teacher has some parameters: a b, PSD metrics, and d is the input dimension. So the problem is sufficiently simple, so we can write in one level. It's sufficiently complex because the matrix B can be very complicated. I should think of this as a teacher, as a student. So the student is a neural network with an input layer, a hidden layer, and an output layer, and it computes the function which is written there. Okay, so it featureizes the input by doing X transpose times Yj. So J is the jth neuron. Okay, and then it passes that through a nonlinear function sigma, which is the activation function, and then it linearly combines all of these to give you a scalar y hat. And it's trying to tune the wi's and the wj's and the vj's to fit this stuff. Okay, so that's what the student is doing. And okay, you measure how well the student is doing by looking at the distance in L2 norm between the student and the teacher. So this is like you're measuring the test error. And robustness is how smooth is the student. So how sensitive is the student to changes in the input? So that's what you measure by looking at the average L2 norm of the gradient. And so let me just go to the results. Okay, you can normalize things so you can compare more easily. By trade-offs, what we mean is results of relations of the following form. Test error plus robustness error is equal to 1. This means you cannot improve one without degrading the other. You see? So it means, okay, there's nothing you can do. There's no free lunch. Yeah, there's no free lunch, basically. And so a technical note here for the theory people in the audience is all of this is happening in the asymptotic regime where the number of neurons, the number of input dimension goes to infinity at a proportionate rate. Okay, if you change the regime, other things are going to happen. And the results, well, these are the results. So the solid curves are the theory, and the broken curves are practice. And if you look at these curves, so this is 1, this is 1 here, this is 0 here. So if you look at, say, this curve, this sine curve, I guess that's what it's called, and this other curve, you see the cyan and magenta curve, they behave like this. So if you take one and add the other, it gives you 1. So that's a trade-off. You cannot artificially reduce one without improving the other. And you have the same phenomenon in different regimes. So this is for the random features regime, where you only train the output layer and the hidden layer is frozen at initialization. And this is lazy regime where basically you assume that the neural network doesn't move much from its initialization. And they do a Taylor expansion about that, and then blah, 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 blah. So the main take-home message is that the relationship between test error and robustness is more complex than what is usually portrayed in the literature. So people usually say, okay, you just need to train things very well and maybe augment your data set artificially or do some other crazy stuff, and then you're going to get robustness somehow magically. And there are a bunch of other stuff. So what I'm not saying here is, okay, we can show that some parts of this trade-off they hold in much higher generality, even for models that have nothing to do with neural networks. And so I guess I'm 2 minutes out of time. So if you want to go further, so the work presented here, there's a preprint here, so you can find all the details. And this is a follow-up. Okay, there's some other work in the same space that they did 2 years ago, which says if you memorize training data, you're going to have trouble at test time. And yeah, thank you.
Thank you. Thank you, Elvis. Well, the next speaker is getting set up. Are there any questions from the audience? We have a couple. All right. Jungmin, I'm going to go to you first, and then Rana.
Hi. I was
wondering. We need to ask questions.
Hi, I was wondering if you could expand a little bit more on how randomization can hurt robustness. What other first of all, why is that the case, and are there any other alternatives we can use in that case to initialize our networks?
Repeat the question.
So you said that random initialization can negatively impact robustness.
Yes.
Could you give us a reasoning for why that might be the case, and if there's an alternative for how we should initialize our networks?
Yeah, that's a very good question. So basically, there's a line of work by Amit Deniali and Peter Bartlett that showed, okay, so if you look at neural network at initialization, which is initialized the normal way, so IID normal with fan-in initialization, you can show that at initialization, this is going to be sensitive to other examples which are in L2 norm, 1 over square root of d times smaller than a typical example. Okay, so since neural networks don't move much away from the initialization, you can show that if you remain in this so-called lazy regime, you are close to this initialization regime, and so you're going to have all of these bad things with high probability. So you can see this as partly an artifact of this random initialization. If you do orthogonal initialization, maybe things are a bit different. But if you do Gaussian initialization, you're going to have this.
Thank you. This is very interesting and I think also very impactful. And the question I have is, what are your thoughts on the broad research community, thinking specifically of AI, optimizing in what we do for minimizing test error? So a lot of the papers we see out there are really going after that. If I have a better accuracy over a smaller test error, then I'm better and I publish. And really what you are saying is that this damages robustness. So what should we do? And again, broadly, the research community in terms of how should we conduct our experiments?
Yeah, this is a very good question. Actually, you can show that there is so in a broader sense, there are people who have computed Pareto optimal curves between. So it's basically you have a optimization game between these two things, and there might be trade-offs in many places. So what people the general attitude right now is that people optimize for test error and they try to do some ninja tricks to make it robust. Because they think if it's not robust, it's because there's some bug or there is an issue or we can just fix it away. Actually, what the theoretical result the community is showing is that, hey, there's a basic trade-off between these two things. You have to decide beforehand what you want to do. Do you want to have 60% test error and be sure that, okay, you are going to also be robust, and from time to time you're going to make errors, and maybe you call a human operator to look at these difficult examples, or you just want to have 99% accuracy? So my short answer is I think 99% accuracy in the classical sense is not very responsible. We should cap it at maybe 70% and then try to find for the most robust model that has this accuracy in the clean sense. Yeah.
Great.
Thank you.
Aiming for 70% accuracy. That's an interesting proposition. All right, so our final speaker of this session is Dr. Shiwali Mohan, a senior member of research staff at Xerox PARC. She studies the design and analysis of collaborative human AI systems. In 2015, Shiwali received her PhD in computer science from none other than the University of Michigan. So welcome back, Shiwali.
Thank you, Jenna. And can you hear me in the back? All right, so hi, I'm Shiwali. I build and study collaborative human AI systems. And I'm a principal scientist now, so got promoted as part. That's okay. All right, so let's dive right in, right into Intro to AI. Right, this is how we are told agents are built. An agent is embedded in the world, it perceives the world, it takes certain decisions, and then it acts out its own decisions, right? So what's most critical to design this agent is what we call a world model, right? This is what are the important states in the world, what is my action space, and then how do I decide on what's the right action to take, right? So this is critical. But this is not really the final deployment case, right? This is an incomplete picture because almost always there's going to be a human involved in the simplest case. And in the worst case, there's going to be a team of humans involved working with this agent, right? The problem is that the AI science as a field does not have any idea of how to represent the human model, right? Just like the world model, we don't know how to represent the right states, the transitions, the actions, the decisions, right? And this is not just me who's saying it. In the past few years, the broader AI community has agreed to that we don't really know how to model other agents in AI systems and reason with them. And in fact, in 2018, AAAI president issued a call of arms that we have to design human-aware AI agents that model, learn, and reason about human collaborators. So this is what I study. There are three important questions that I really focus on. The first one is, how do we reason about the human collaborator? My approach is that we build a prescriptive model using insights from human-centered sciences. So this would be cognitive science, psycholinguistics, behavioral economics. Then we design the intelligent collaborator, right? So this is not just an algorithm. This is an algorithm embodied in an interface that interacts with the human and can demonstrate some behavior, right? And the third thing is, how do we measure progress? Because as computer scientists, like the computational-centric metrics are very attractive to us, right? It's it's scaling, it's accuracy, it's efficiency. But once you deploy these systems with people, they don't care about any of it, right? So we have to really learn what does it mean for us to build a good AI system. And again, I go back to human-centered sciences and understand how they run experiments and then bring that back to AI system design. And if you do this right, like you can have a broad impact, right? From AI systems, cognitive modeling, to human-machine interaction, and to, in fact, even in the domain. So some of the work that we did for health behavior change was part of the medical information sciences community, and they really appreciated that approach. All right, so in interest of time, I'm going to run through 3 different collaborative human AI systems, and I'll highlight what's most exciting for me in them. And then you can feel free to approach me at the poster, and then we can talk more. Right, so the first one was funded by NSF NIH Smart and Connected Health. The premise of this work is that behaviors that are rooted in sedentary, unhealthy lifestyles impose major costs on healthcare. Right, so we thought that, hey, maybe we can build an AI health coach. And the success of such an AI health coach is crucially dependent on understanding how do humans learn, how do humans gain new behaviors, right? So here we touch with cognitive science. So we brought to bear a common model of cognition to then design or identify a set of desiderata for what different types of interfaces an AI coach must implement so that it can support people in building new behaviors. We extended it to model-based reasoning, where we designed this long-term AI health coach that could live on for months and then slowly help you build behaviors, right? So the most exciting part about me was to be able to run this longitudinal ecological study with an AI system, right? Usually the way either the AI systems are very transactional, right? You give them an image, they'll give you a label. Or the other way to study AI systems is to bring people in the lab. So here, we actually sent people back home with an AI system in their pocket on their mobile phone. And we studied the behavior of the AI system for next 6 weeks. Right? And we were able to measure how effective it is. So that was my mind was blown that you could actually do that. The second project that I wanted to bring up was on sustainable transportation. So this was done on ARPA-E Transnet. And the premise for that project was that transportation is one of the largest consumers of energy in the United States. Congestion wastes time and fuel. And this is a technology and a policy problem, right? So they wanted us to build a system that could influence people to take more energy efficient, sustainable modes of transportation, right? So now you can bring all your complex, fancy optimization algorithms and find the most energy efficient way to get from point A to point B. But if if that solution is not acceptable to the human, they are just going to go back to driving, and then you basically have done nothing, right? So here we engage with rational choice theory from behavioral economics. We understood how each choice can be projected into the utility space. And when we are asking people to take a sustainable mode of transportation, we are asking them to pay a switching cost, right? And it's that switching cost that's important for someone to accept that solution, right? So we built a machine learning model for it, we validated it with human data, we embodied it in a system, and then we were able to show that if you follow these principles, if you did acceptable planning in a transportation network, you would be able to reduce energy and delay. And the final project is interactive task learning, my absolute favorite project. So this actually began at University of Michigan around 10 years ago when I was part of the SOAR lab. And the main premise of this project is, well, how can we design machines, robots in this case, that can learn with humans and maybe teach humans, right? And the related project that I led at Park is DARPA Gala. So this is asking this more fundamental question of, well, how do agents learn language? And where does meaning in language come from, right? So we are pursuing this really strong hypothesis that for language to become meaningful to agents and to help agents communicate with humans in natural language, the way you would understand language is by associating it with the world models that you have and you use to operate in the world, right? And so the most exciting part for me in this is actually work done by graduate student Preeti Ramaraj at University of Michigan, who conducted this study on how humans use language to teach maybe a learning agent. And she found some very interesting things. So the first one was, well, the humans, it's tendency to think that humans will just provide data to a learning system, right? But we found that humans actually provided a lot of structure, and they were able to teach the entire domain ontology, starting from object properties, through method of action, until tasks, and they were able to teach in the entirety of it, right? So that just means that we have to exploit it. We have to exploit that structure that's available in human teaching. The second very interesting thing she observed was that human interaction was extremely intentful, right? So the humans expressed a variety of intents using language. So sometimes they were trying to inform the agent, trying to teach it, trying to introduce it to a new concept. But once they had taught that concept, they tried to evaluate the agent, right? They're trying to understand the boundaries of competency. And once you figure out, okay, the agent is not competent enough in this specific dimension, they then switched to, okay, let me try to revise what I said, right? So there's this entire diagnostic and training process that humans engage in using natural language, and that sets the stage for how we should be thinking about language models, right? So that's I think it's a super interesting finding. All right, so I'm towards the end. We have focused on this particular part that once you design an AI agent, it's going to go out there and operate in the world autonomously. But if we really want to exploit the full possibility of AI systems, we have to think about all the different ways humans and AI can collaborate so that we can solve a wide variety of problems. And this is what I want to do. Thank you.
Questions for Shiwali?
Well, thank you. First, it's great to have you back here.
Thank you, Radha.
And it's really very exciting work. And I really think that the future will be in this kind of interactive learning. And one question that comes to mind also, informed by previous somehow negative experience we had with such systems, is how to guard against malicious use. We, of course, assume all good intentions that you will actually want to teach these agents, but sometimes it happens that people would use them, say, adversarially. So how to guard against such uses?
Right, especially in the cases when humans are teaching the system. I mean, I would confess that I haven't really thought very deeply about it, but I would imagine that there would be, so we have very specific task representations that once it gets learned, you can actually inspect, right? So you can reason about them further. A human can look at it. Usually AI modelers can look at it. So that's one way is that whatever has been taught can be inspected by a third party to see if it's ready. The other part of having a very explicit task representation is that the agent can do a self-introspection and run the models forward to see what world states would arise if it applied that task in that specific context. And then there could be some constraints, safety bounds put into the system itself that if it's leading to states that are negative or harmful, and they have to be like defined a priori, then it will not execute those tasks. So, right, so you have to think about the design space there as well.
I very much like and agree with the notion that in order to teach and give meaning to the language, you have to ground that, the teacher has to ground that in the world model. But what if the world model fails to include some key concept? And so part of the teaching is to help the student acquire a new concept in the world model. Right. How do you address that?
Right, so that's a great question. So that's what actually Preeti found, is that humans engage in this back and forth of, okay, let me teach something. Now let me try to evaluate what you have learned, right? By setting up specific context, scenes. And what that does is it exposes the bounds of competency of the agent, so it might fail in certain states. Right, and now if you design the agent right, you can refine it. The other part of the agent design part of it is what we have built, at least the way we are building it, is this metacognitive reasoning process, which keeps into account where exactly it's failing, right? So you could imagine a world model having sub-models underneath it. So there's a visual sub-model, there's a spatial sub-model, there's an action and a task, right? So as it's composing knowledge in each of these to do a task in the environment, it also maintains some metacognitive information about if this model is failing in this. So once you know, right, then you know that that's where you can localize your learning. That's where you need to advance the interaction with the human and then learn in that specific model.
Great. And a big thank you to all of our AI